Hey, it's me again. So you've already seen how to calculate the moment of inertia of a long thin rod about its center, but let's say I want to switch it up for the second show and spin it around this end instead. Whoa. So this is the exact same stick we're talking about. It's got the same mass, it's got the same length, but when I spin it about a different point, it doesn't have the same moment of inertia. So how are we going to figure out the difference in moment of inertia from here to here? So we got a similar question here, except now it's rotating about its end instead of its center of mass. There are a few ways you could tackle this one. You could just set up the problem the exact same way again, except this time you're integrating from 0 to L, rather than from negative L over 2 to L over 2. That makes the calculation actually a little bit easier, because we'll end up with lambda times r cubed over 3 evaluated from 0 to L. And that'll simply just be lambda times L cubed over 3. And when I replace lambda with good old m over L, that'll be m over L times L cubed over 3. That'll simplify down to 1/3 ml squared. And that's exactly what it is. But there's another way you can solve it as well. This is something called the parallel axis theorem. Now, this is an equation that's actually not on your AP sheet. So this is one that honestly is probably going to be good to memorize. And here it is. It's basically saying that you can find the rotational inertia. If you know the rotational inertia around the center of mass, you can find it at any other point. Here, ICM is the rotational inertia about the center of mass, m is the mass, and d is the distance from the center of mass to your new pivot point. For our example, initially this was rotating about the center of mass, and we found that the rotational inertia about the center of mass was 1/12 ml squared. That was in the previous video. Now, we're going to move that pivot point to no longer be here. Now it's going to be moved to over here. That distance right here is simply going to be L over 2. So let's find the new center of mass using the parallel axis theorem. That'll be 1/12. Oh, here, let me rewrite the parallel axis theorem out real quick. ICM plus MD squared. In our example, that'll become 1/12 ML squared plus M times D being L over 2 squared. I end up with 1/12 ml squared plus 1/4 ml squared. As you add fractions, you got to find a common denominator. So this is going to turn into, let's see, 1/12 ml squared plus 3/12 ml squared. Well, by golly, that's 4/12 ml squared, which is simply 1/3 ml squared, which is exactly what we got doing it the calculus way. So the parallel axis theorem can be really helpful in finding new moments of inertia a little bit faster without having to go evaluate an integral again.